Hello, and welcome to Unnatural Numbers, the YouTube maths chat show where we chat maths about YouTube, or something like that. Today is episode 3, and so we're going to be talking about the number 3, the third of all natural numbers. Is the number 3 magic? Well, let's find out. I'm going to be your host today. I'm Benjamin Cornish. I'm well over 30% of a real mathematician, and I'm joined today by some lovely guests. We have Christian Lawson-Perfect, who you'll know most famously from episode 1 of this chat show, but you might also have seen him as the co-creator of the Aperiodical magazine. Welcome, Christian.
Hiya.
Hello. And we've also got Hope, who is a student at Leeds University, currently studying for their PhD in set theory. So that is very impressive. Welcome, Hope.
Thanks for having me.
Fantastic. So let's get into talking facts about numbers, up with the number 3. And first of all is my fact. My fact today is that 3 is the first prime. Think of that. Any objections?
I've been well trained to have some objections to that, yeah.
Okay, so as we discussed in episode 1, the number 1 is, of course, not prime. In episode 2, we also all agreed that 2 was not prime, although I had to edit that bit out because of the big conspiracy us mathematicians have about not telling the general public real facts about numbers. And I'm going to say 3 is the first prime, but of course it's not the first prime number. 3 is, in fact, the first prime not. And I don't mean not number, I mean it's the first knot with a K. Today, I'm going to be talking about how to tie knots, or more importantly, how a mathematician might tie a knot. So I'm going to show you 3 of my favorite knots. Here they are. And what do you notice about those? Are they quite fun? Is that how you might tie your shoelaces?
It's a closed loop. Well, they're all closed.
They are closed loop, yeah. So when a mathematician talks about a knot, it's not actually trying to fix together 2 bits of string or hold anything down. What we're interested in is if we take a continuous loop of string, how many ways can we arrange that? How can we make it weave in and out of itself to form something that we might call a knot? But if we're going to think like a mathematician, what better place to think than in knot theory? Because one of the big questions that we ask ourselves in all of maths really is, what's going to be the same here and what's going to be different? How are 2 things alike and how can I change from one to another? So I've got these 3 knots here and I'm going to ask you a big question. Are they fundamentally different from each other or are they fundamentally the same but just wiggled around a bit?
So this depends on what sort of wiggling, I guess, we're allowed to do, right? So whether we can kind of pull things through and deform them into one another.
That is a fantastic question. Yeah, how are we going to wiggle these things? And really the answer mathematically is just as intuitive as if they were made of actual bits of string. So some of our rules that we have in knot theory is that we can bend them and twist them and pull them and stretch them. And the actual shape of the knot is not important at all. It's only about how it interacts with itself. And just like with real bits of string, we are not allowed to pull it through each other. So these are physical objects that can't pass through themselves. And so it's all about how they've been braided together that makes them the same or makes them different. So we've got some rules. We can't pull them through each other. We can't cut anything and we can't glue anything back together. And our job is to work out whether knots are going to be the same. So I'm going to show you another of my favorite knots. And I'd like you to see if you notice anything about this knot here. So this knot here, is this going to be the same as the ones above or different to the ones above? And again, that's more of an intuitive answer because it's difficult to see immediately whether it's the same to those 3, isn't it? But what's your gut telling you? Same or different?
It feels different. It's hard to tell where there's a move you can do. And are you going to direct me towards counting the number of crossings?
Well, you can read the word crossings just underneath. Yeah, I will be getting onto crossings in a little bit. But I'm actually going to immediately break one of the rules that I gave you a moment ago. Because what's the point of rules if we don't immediately break them? I told you that we are not allowed to cut the string and glue things together. But if I do that very same thing, if I cut the string, if I pull this apart over there, oh, look at that editing, then you might start to notice something interesting. What do we notice here? Maybe this would help if I get my pen out. I'm going to try and match the colors. Perfect match. If I do this, can you see anything that is now more obviously the same as one of those 3 that I showed you above?
Yeah, so
I label them
like
A, B, and C. Yeah, so these are now both very, very similar to that first one, aren't they? So here, we've now got the idea of what it really means to be a prime knot or a composite knot. So our prime knots are going to be the knots that can't be built from other things. And composite knots are ones that can. So this knot that I showed you originally, by the way, it's called a square knot. This square knot we say is composite because it can be made up of two lots of knot A that have been joined together. And for that reason, I can tell you that it is 100% different to knot A, knot B, and knot C. Because knots A, B, and C are all prime knots. They can't be composed of something else, whereas this square knot can be. It's two dots of knot A. Okay, so that is breaking the rules of cutting strings and joining things together. But what if we definitely don't cut string and join things together? What if we are just interested in whether things are equivalent? We talked about how we might move things lawfully without breaking rules. And here we get one of the coolest sets of moves ever developed, the Riedmeister moves. So in the Riedmeister moves, these tell you how we're allowed to arrange string. And there's 4 of them that we're allowed to do. We're allowed to change the general shape. So this is a wiggler. We're allowed to untwist a simple loop, so the twisty-twisty. We're allowed to slide 2 things that pass under each other away, or over each other, away from each other. And then also slightly more complicatedly, we're allowed to slide one string that is behind underneath the crossing point of another. So this one's a little bit more difficult to describe, but you can see that curly one at the back has slid downwards behind the one behind. Now, this is hopefully fairly intuitive because these are things that you would do with actual bits of string or headphones if you were trying to untangle them. But with just these 4 moves, we can now say which 2 knots are actually going to be equivalent to each other when we can, without breaking any rules, turn one knot into another. So would you like to know the method for how we can tell which 2 knots are equivalent?
I would, please.
In which case, go do some research on knot theory. It's still an outstanding question. Nobody knows when things are going to be the same. For some simple knots, it's relatively easy to show, but as we get into slightly more complex knots, it becomes incredibly hard. And there is no single way of showing how to move one knot into another form to check that 2 things are equivalent. So another question mathematicians like to ask themselves is, if these things are the way it changes, what sort of things stay the same? And for this, we might turn to the invariants of knot theory. There's a few invariants that we might be interested in, the stick number or the bridge number, but one that I'm going to draw your attention to today is the crossing number. So the crossing number is a nice, simple way of checking if a knot is going to be the same, and it is to count the number of crossings. If we have turned our knot into the simplest possible diagrammatic representation of a knot, then the crossing number is invariant. So here, this knot here, which I keep talking about as knot A, maybe I should give it a name. It's called the trefoil knot, or at least that's how I think you pronounce it. This has 3 crossings, so its crossing number is 3. If we zoom in a little bit to knot B, we can count the crossing numbers of B to check to see if it can be turned into A. And B has 1, 2, 3, 4. It definitely cannot be the same as A. There we go. So we've got an invariance crossing number. But that doesn't always tell us if 2 knots are equivalent. And I'd like to invite you to have a bit of a pancake flip. I'd like you to imagine you've got this knot in front of you on the table. You put your spatula underneath and you flip it around to make it look like that. First of all, let your eyes acclimatize. Can you confirm for yourselves that these are different knots?
We need to go back and say what's the same and what's different again.
What's the same and what's different? So these knots have orientation to them. That is, the direction of these has affected the knot. And for this, it might be helpful to pick a point on both knots. I'm going to go here and start measuring what happens as I move clockwise from this point. And first of all, we get to this crossing point here where we have gone over, and I might describe that with a plus. But here we get to a crossing point and we go under. So I'll describe that with a minus. And then the next one is going to be over here and under here. This one went over and this one went under. So they are definitely both alternating. But starting from this point, the alternation is going in the wrong way round. one has gone plus and one has gone minus. So not only is the crossing relevant, but also this idea of over or under is going to become important. And I'll share a fact with you. These two are very much distinct knots. You can test this for yourself, and I'll leave this as an exercise for the viewer. If you were to only apply the Reidemeister rules that we described above, you could not turn one of these knots into the other knot. It's impossible. Here's a question for you. Do you think that all knots that have been flipped are uninvertible or not equivalent? Do you think you can ever get an equivalence between knots that have been flipped?
If I have a circle, that's a kind of knot, and if I flip it, I've got the same one.
Indeed, yeah. So a circle does not have orientation. It's not chiral. So some knots can be flipped, and the flipping doesn't even make sense. But what about a knot that has an ability to flip? Can you always tell if that knot can be converted back into the other one? The circle is, of course, a very easy way to check. But if I gave you something more complicated, say I gave you the knot that we met at the top, if I gave you knot B, could you be able to tell if knot B turns into itself on an inversion?
I feel like 90% of the time when you ask a question about knots, the answer is we don't know yet.
Nobody knows. Yeah, so there is no way to check whether a knot will always be self-inverse. No way to check whether flipping it over like a pancake will be able to give you the same knot or a different knot. No one knows. If you want to find out, go do 20 years of research into knot theory. Someone needs to. Okay, so I think we've got challenge time now. So for challenge time, I'm going to ask you to design a knot of your own. Christian, you mentioned the circle earlier. I think I might decide that a circle doesn't count as a true knot. In fact, in knot theory, we call the circle the unknot because it's not a real knot. It's kind of like the base case. But I'd like you to design a real knot that only has one crossing point.
Well, I can try. I don't have a graphics tablet, but I'm going to use this horrible tracker.
Now, I put it to you that you guys have actually just drawn the same picture as each other, and indeed the same picture as me. Because really all we've got here is Reidemeister's twisty rule. It's going to be difficult to imagine this in 2 dimensions, but you can try this at home. If I take this arc and pull it up there, and this one and pull it down there, that will untwist, and you're back to the circle. Hope, I'm afraid you've also failed the challenge, because this one is going to come down there, that one's going to go up there, and same on this side, that's going to come up, and that one's going to go down, and again, you've landed at the circle, the unknot. You can play around with this, especially the two crossings. There's a few different ways you might try to generate two crossings. You can play around with that at home. But what you should find is that every time you try it, you will get back to the unknot. And that means it's impossible to do. Therefore, I put it to you that the very first knot that can be made must have 3 crossings. And indeed, I can demonstrate this with the one that we've got over here. And we call this the first prime knot. It cannot be created by other knots being glued together, and it has 3 crossings. Therefore, 3 is the first prime knot. Now, the other thing mathematicians like to do is we like to organize our understanding of something. It's one thing coming up with some definitions and rules, one thing asking when does something change and when does it stay the same. But what about if we take everything that can possibly exist and try and put it into like a periodic table of things? We've got the periodic table of numbers, of course. It's just a number line. What about the periodic table of knots? Well, I'm glad you asked, because I've got one here for you. These are the first 15, in fact, prime knots. So none of these can be created from other knots. If you cut and glued together other knots, you can't make them out of other things. Therefore, they are, in a sense, unique. We call them prime. And would you like to know how many prime knots there are, at least as far as we know?
Go on.
We have 2,199,471,680 known prime knots. And this is only testing up as far as 20 overlapping points. Now, I've got some headphones with wires still, and I definitely have had knots with more than 20 crossing points. And yet there are millions and millions and millions of ways of creating a knot with just 20 crossing points. And what about 21? What about 23? Why does it stop there? It's because we literally don't know how to go any further yet. The computational power needed is not yet with us, and we need someone to go and do 20 years of study in knot theory to go and figure it out.
The one thing I know about knot theory is I know the most simple fact about knots. If you draw a curve on a piece of paper and it can wiggle around, and whenever it's going to cross itself, you always go under.
I think you're about to tell me that this turns into the unknot.
Yeah, so then join it back up again. It has to be the unknot.
Yeah. Is this to do with the bridging number?
I would give a much more straightforward proof of it.
Good.
So imagine you're drawing, like that, you're looking down on that from above, but imagine the whole time you're drawing, you're also going down.
Oh, yeah.
Every time you cross, you're of course going underneath where you've been before. And then at the very end, you go straight back up to where you started.
Oh, that is lovely.
So that piece of string, you can just pull it taut.
Yeah, I think what you're describing here is that the knots that we think of should actually exist in 3 dimensions, but whenever we draw them, it's only ever a 2D projection of a knot theory, of a knot, sorry. But yeah, that's a really lovely visual proof of that one. Nice, I like it. We know for a fact that for any 2 knots that are equivalent, the complement of those knots, that is all of space that is not the knot, must also be equivalent. That's a fact. But it is not yet proven in the other direction. If you have 2 complement spaces that are identical, and I think the word we might use is homeomorphic there, then we don't know if the knots are equivalent.
Really interesting.
It's just endless unknowns knot theory.
I would put a lot of money that that's true. I just don't think it's yet been proven.
I have a feeling that knots are like one of these things that our brains just aren't wired up to really think about now. Like knots and probability, we just can't do it. And so things that should be simple theorems, we're not there.
Hope, what was your flirtation with topology?
Well, it's a field that is reasonably linked to set theory. There's a conference that I've been to a few times where a bunch of set theorists and topologists kind of go off into genuinely a monastery in the mountains in Czechia and do maths together for a week. So topologists are kind of part of the same very pleasant cult of mathematicians that I'm also a part of.
It really sounds like you're telling a joke, though, that some set theorists and topologists go to a monastery in Czechia, and then I'll think about the punchline for the rest of this episode.
The group theorists that I once mingled with, every year they would go off to a Swiss skiing resort.
Have you ever been speed dating with group theorists? So every time the bell rings, they all have to rotate by 1 space around.
Sure.
Okay, so with that, shall we move on to our second fact of the evening? And Hope, that is your fact. What have you got for us today?
Yes, absolutely. So for you, the number 3 was the first of something. For me, number 3 is the last of something. So what I'm going to be talking about is that 3 is the maximum number of circles or categories we can have in a Venn diagram. So I think the really important thing to start off with is what do we mean by a Venn diagram versus an Euler diagram? So this is what these first couple of diagrams in colour are meant to illustrate. So these 2 diagrams, the bunch of circles on the left and the bunch of circles on the right, are expressing the exact same information. So what they're expressing is for these sets A, B, and C that I have written out, what the overlaps are. So we can see that the number 1 is in the set A and in the set B. But in our Venn diagram, we are expressing all of the possible overlaps. So in our first thing, this bit here of our Venn diagram expresses the fact that there could be something in 3 sets that is in A and B, but not C, or A and C, but not B, as I think these are set out. But with our 3 sets, A, B, and C, that isn't the case. So sometimes these Euler diagrams, which don't show every single possibility, can be clearer in terms of expressing information. So what do we have in A, B, and C? But in terms of expressing, okay, what are the possible overlaps for these sets A, B, and C, a Venn diagram will show you everything that we can do. So you probably will have seen, just as ways of expressing information, Venn diagrams with 2 circles, maybe 3 circles. But what I'm asserting is if we move to 4 circles, it cannot be a Venn diagram anymore. Okay, so one of the important things that we're going to talk about is kind of how many disjoint regions do we have in our Venn diagram. So for this one on the left here, how many disjoint regions do you think I have, either of you?
I can see you've coloured in 3 things.
So I have been quite sneaky with what I've coloured in. Is there any other possibilities that you can note?
Well, I know that my GCSE students that I teach are going to be raging at this at the moment because these first Venn diagrams that you drew didn't have a box around the outside. So is that box important?
Yes. So we are also going to class this outside bit as a region. So if we think about, bits of information that a Venn diagram would represent, we can quite have the case where, is it A, is it B, is it both, or is it none of them? That's always a possibility. So this kind of being in the box is something that we count as one of the regions. The takeaway is for this on the left, we have 4 regions. So
Okay.
1, 2, 3, 4. So on the right, we can do the exact same thing. So, okay, we have 1, 2, 3, 4, 5, 6, 7, 8 regions. So when we have n equals 2, we have 4, but n equals 3, there are 8. Can you guess the pattern here?
So it's got to be 2 to the power of n.
Yes, 2 to the power of n, exactly. So this is basically the number of possibilities that we're going to have as our sets go up. So say rather than A, B, and C, if we had A, B, C, and D, then we would have 2 to the 4 amounts of possibilities. So is it in none of them? Is it in A and D? Is it in A, B, C, but not D? So essentially, the reason that we can't have a Venn diagram, so something that shows every possibility for n equals 4 and above, is because we can't arrange these circles in a way that overlaps to show all 2 to the 4, so 16 possibilities.
Is that something that we should all have a go with now? Because I feel like that should be intuitively quite easy to do.
So yeah, why don't you have a go at overlapping 4 circles and see how many regions you can come up with.
Oh, there you go. Oh, hang on, I need to get those 2 overlapped as well. Oh, there you go. What's wrong with this?
So if you count those up for me, how many different regions do you have?
I would love to. I'm going to use my thinnest pen and go for 1, 2, 3, 4, 5, 6, 7, 8. I come from the school of thought that says count them in any order you find. 9, and then those are a bit too small, but we've got 10, 11, 12, 13, and 14, yep. The one on the outside. Ah.
Exactly. So if you were to wiggle these around, you can find 14, but there is no way of doing this with circles where you can get 16.
Can you tell me which ones I've missed?
So the diagram that you've shown here, if we look carefully, if we want to say something is in B and D, but not A and C, there is no way of indicating that on the diagram. So it's the same thing happening for A and C, but not B and D. So we have 2 things that are missing.
That makes sense, because in the morning I like to eat Doritos and bread, but I don't have apples and carrots.
Exactly, there we go. So we can kind of see intuitively just by messing around with 4 circles that we can't really find a way to rearrange these to get all 16 possibilities. So have mathematicians found a nice way to show that this happens for higher number n. Maybe 4 is just a weird outlier. And they have. What I'm going to be talking about is a sketch of the proof, the maximum number of disjoint regions in the plane, so these separate sections formed by n circles, is going to be 2 plus n squared minus n. Okay, so the first thing that we need to do is observe that no 3 circles can meet at the same point. So what do I mean by this? If we look here at this kind of meeting point, we have 2 circles meeting at one point. So what would happen if we tried to have 3 circles meeting there? What would be wrong with it? If we wanted it to meet at the same point, well, then we don't have all of the overlaps that we need. This circle would have to be up here for it to be a Venn diagram, for us to be able to see all of the possible overlaps. So again, we only have 2 circles meeting at any point. We try and have 3 circles meeting at the same point. It won't be a Venn diagram anymore. Okay, so what we then want to do is consider what is the maximum number of these overlap points. So if you're adding your nth circle, so this is going to intersect the other n-1 circles in exactly 2 multiplied by n-1 points. So maybe the kind of easy way to illustrate this is on our n equals 3 example, this one on the right. So for our third circle here, if we just have 2 circles and we add back the third, how many points of overlap does this have with the other circles? Okay, overlaps. Well, n is 3, so this is 2 times 3 minus 1, so 2 times 2 overlaps in 4 points. We started off by talking about these overlapping points, but the important thing for us to consider is the disjoint regions, so the spaces that are created by these overlapping circles. So if we think of kind of any 2, consecutive overlap points that we've added on our nth, our final circle that we're adding, what's happening between those points? They're creating an arc. There's going to be some curved line that is going to divide an earlier region into 2 regions. So all that we really need to observe is these 2 times n-1 overlapping points that we add in our nth, our final circle. They add 2 times n-1 regions. So again, with this example, so we added this last circle and we added 1, 2, 3, 4 regions. So the amount of overlapping points that we add with each circle corresponds to the new regions that we add.
So every new circle cuts all of the other places in half.
Yeah, essentially that's
Or in 2.
the way to think about it. Yeah, so for the new circle, it will kind of overlap with the circle at 2 points and cut it in 2. So these 2 things correspond exactly. So we've been talking about what happens when we add our nth circle. So to figure out how many regions we're going to have in total, let's sum up the amount of regions added by all of these n circles. So, okay, for one circle, we have 2 regions. So that's just inside the circle and outside the circle. For a second circle, we have added an additional 2 times 2 minus 1 regions. So if we do this all the way up to in circles, that's represented here. We have 2 plus 2 times 1 plus 2 times 2, etc., all the way up to 2 plus 2 times n minus 1. So, okay, we can rearrange this and quite easily get 2 plus 2 times brackets with 1 plus 2 plus 3 plus all the way up to n minus 1. Now, there is a neat trick that I'm going to use here, which comes from a kind of fairly famous story about a mathematician. I wonder if either of you have heard of this before.
This is young 7-year-old Gauss, I believe.
Indeed, it is. Yeah. So the story that we're both talking about is Gauss's teacher, kind of, I think, as a way to keep the kids quiet, being asked to add up all of the numbers from 1 to 100, and he did this very quickly. So essentially, we have this formula. If we're adding up n things, n times n plus 1 divided by 2. So the thing to note here is that we are summing up to n minus 1. So this ends up being n minus 1 over 2. So this is using Gauss's summation formula. And if we rearrange this, what we get is 2 plus n squared minus 2. So if we do this in a maximal way for n circles, the maximum amount of different regions we can get is 2 plus n squared minus 2. And if we compare this to the 2 to the n possibilities we have, these Venn diagrams just don't work for n that is greater than 3. So plugging in for here, we get 14. So what you drew before, Ben, is optimal. It's just not a Venn diagram.
Thank you very much.
So what I will end you on is, okay, what are some ways of representing this information, the different possibilities? Because we can do this pictorially. It's just not a Venn diagram anymore. And what I will show you is for n equals 4 and n equals 5, one way of doing this. Of course, there are plenty of different options, but if you go through and count up, this will correspond exactly to what you get with this formula that we just derived.
I mean, I've got some skepticism here because I was fairly sure that your fact and your proof was going to be all about how we can't use circles and we have to use other shapes. And I can see that you've got some non-Venn diagrams that are drawn with these sort of loon shapes, but there was nothing in the proof that you described that said it had to be a circle. I was expecting some kind of x squared plus y squared equals r squared circle equation, but your proof seems to just describe cutting things up in an arbitrary way. So why is it that the proof doesn't also apply for these shapes?
So one of the kind of important things to note, and so I got this proof from a really great open source paper called "Is the Venn Diagram Good Enough?" And one thing that I skipped over the details with a tiny bit is this kind of no 3 circles can meet at the same point. And there's an argument there in terms of the radii of the circles. And it's that bit of the proof early on, when we don't need all of our shapes to be circles, that bit of the argument doesn't quite apply anymore.
Okay. All right. So we can still represent the power set of different sets using non-circles.
Yes, exactly.
And is there an upper limit to this?
Can we go on creating shapes with more and more overlaps? Yes, we can.
So that moves us on to our final fact of the evening. And Christian, that is you. So what have you got for us tonight?
So I'm thinking about numbers. It's a podcast about numbers. And one thing you can do with numbers is break them up into smaller numbers. So you could just ask, what's that question? Like, how many different ways can I split a given number into some smaller numbers? That's integer partitions, and there's some really good stuff behind that. But if you restrict yourself to just a few, like a subset of the possible numbers, and then you can ask some really good questions like, is it even possible? Can every number be written as the sum of square numbers? What do you reckon?
Oh, I reckon no.
I also reckon no. I feel like I've seen some facts about certain years being able to be expressed in terms of square numbers, and I don't think it'd be a good fun fact that applied to every year.
I think there's more numbers than there are square numbers.
Okay, I'll remind you that 1 is a square number, and I didn't say distinct. So like 7 is 4 plus 1 plus 1 plus 1. Fine. You can't write every number as the sum of distinct square numbers. 7 is, you get 4 plus 1, then you're stuck. Right. So that's the game. Let's pick a subset of the natural numbers. Let's try and write every integer as the sum of... How many do you want?
I want 5.
You want 5?
Oh, 5 on numbers.
Hope, can you beat that? Can you haggle down?
Oh, if you allow me to use it as many times as I want, I can think of one odd number that I can sum to make any number you like. Yeah.
So if I give you the number 100, which odd numbers would you use?
I, as long as it doesn't have to be distinct, then I can just do one plus one plus one plus 100 times, right?
Well, I've got 5 numbers to choose from, so I'm going to take 50, 17, 19, 21. Oh, no, that's not going to work.
You're thinking far too hard about this. So in general, how many odd numbers do you think you need in the worst case?
Worst case, 2.
So two, yeah.
Two. Yeah, it's two. Nice, easy one. Can you write every integer as the sum of prime numbers?
I know a fact about this. If we do multiplication,
All right.
you can write every number as the product of prime numbers. How many primes can we have?
How many do you want?
No, again, there's just more numbers than there are prime numbers. You'll never get them.
That's true, but if you've got some number, there's enough different prime numbers underneath it. There's a lot of combinations.
I can't write one as the sum of prime numbers.
It's still conjectured whether for every even number, you can write it as the sum of two prime numbers.
And this is the famous Goldbach conjecture.
That's Goldbach's conjecture, yeah.
Ah, of course. Okay.
So if that's proved, that's big news.
And you want us to do that now?
Tonight I will prove it. No, okay. So we think maybe you need two prime numbers. That's all to write any even number. Right. Here's a pretty weird subset of the natural numbers. I'm going to move this. Right. Every integer has the sum of palindromes. So a quick reminder, a palindrome is something that's the same when you read it forwards as backwards. So string of digits for a number, you're gonna write one, Ben, are you?
Yeah, 27,972.
Yep.
And I'll put
That's
a
a good
comma
one.
in there. Yeah.
The comma breaks the symmetry though.
I know, but it causes such juicy arguments in the comment section.
Yeah. Okay, 27972 or backwards 27972. That's the idea. Right. So if I give you any number, not necessarily a palindrome number, how many palindromes do you want to write it down to sum up to that target?
It can't be done.
It can't be done
Not enough palindromes.
in general.
There's far more than any numbers than palindrome numbers.
As long as we're allowed, one being a palindrome, you might need, or just the number 9 being a palindrome.
Yeah.
That doesn't get it you quickly, but we could make every number with some amount of palindromes, I think.
Yeah, exactly. So it can be done for every number, unlike with the primes. If you allow repeats, pick the absolute worst one, number 1, and just have loads of it. Is there a limit on what the worst case could be for how many you need? So is there a number that needs too many?
In base 10?
Yeah, sure. Well, okay. So what if I told you that you needed 49 palindromes?
I'd say you've preempted what episode number we're on by about 46.
Yeah, that's no good at all. This is episode 3. Right. So a few years ago, there was a paper, every number is the sum of 49 palindromes. Somebody had thought this problem, written down, thought, well, I can do it with 49, and published a paper about it, which, of course, is begging someone else to go, I can do better than that. So someone did do better than that, and they wrote the paper, every number is the sum of 3 palindromes.
Wow.
Gosh, they must have been kicking themselves, the other guy.
Yeah, well, I think they got on quite well with each other, actually. But yeah, so this, I think, is an amazing fact because I think, Ben, you were right. It doesn't feel like it should happen. Palindromes, it doesn't feel like you've got enough wiggle room, enough choice to be able to do this. But you can. So I was so astonished by this a few years ago that I needed to understand it. I tried to read the paper where they give the proof, and I can't recommend it. It's a really, really bad one. It's a proof by cases, which means that they sort of break the problem down into, well, if your number looks like this, then we do that. If it looks like something else, then we do something else. There are dozens and dozens of them, and they're all really complicated. But I thought, well, I'm going to write a program to do this. If they've given me this proof by cases, they've shown me how to do it, I will do it. So I did that. I made a web page, and we can now scroll down to it. And I so loved this that I wanted this page to big up how cool this was. So it's we can go through it. I can write any positive number as a sum of three palindromes. That's what a palindrome is, just to remind you. Yeah, I really can do it for any whole number.
You're so confident you put all these slides together.
I have to do it in an old-timey ringleader voice. Right, so why don't you put in your number, Ben? Yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9.
Oh, right. So I thought you were going to use this and do this manually, and I was going to be incredibly impressed.
I can't do it manually. I had a thought earlier today. It's like, can I get my head around this enough to do it live? And absolutely not.
Okay, so should I click on the
Yeah, click on that.
abracadabra?
Abracadabra. So it's going to
Almost.
show us. It's going to pick some palindromic numbers to add up here.
Right.
Okay, first one is a palindrome.
Yeah.
The other one's a palindrome.
So is there any pattern to those palindromes?
They're all
Because the number I
palindromes. That's the
gave you,
pattern.
well, the number I gave you definitely had a pattern, as ascending numbers.
No, there isn't. If there's a pattern, it's really, really hidden. It's really obscure. So just like there was room to improve on the 49 palindromes, there may be room to improve on this algorithm for there we go. This algorithm for breaking it down. For lots of numbers, you can choose which palindromes you want to use. I don't know if that was true for this one. So it may be that there's an algorithm that chooses different numbers but works better. Yeah, so you can do this all day.
I was expecting more of a pattern on that. Hope, do you want to be in the driving seat? What number do you want to pick?
Let's do 3, 2, 1, 1, 2, 3.
So you are going to pick a palindrome. Does it have to do it in 3, or is it going to cheat and give us just one answer here?
It's probably going to say 3, 2, 1, 1, 2, 3, and then a couple of zeros. Yeah, there we go.
Okay, all right, fantastic.
I've had a few angry emails from people saying, "Oh, you're cheating if you're using zeros." And I was like, "Well, really, that just represents the fact, like, you don't need 3 for that one."
Go on, Hope. Do you want to pick another one?
2000.
2000.
Okay.
If either of you can do one of these in your head before the computer does, then I'd be impressed.
So I'm going to put in 2015 because that is the year that the 49 palindromes was published. And I think it's really exciting to remind people that that new math is still happening all the time. A lot of the maths that we teach in school was from hundreds, if not thousands of years ago, but people are still doing new and exciting things. And you can join in too if you go off and do a maths degree and get a PhD and do fun stuff. But if that was 2015, Christian, when was the 3 palindromes published?
Annoyingly, the very next year.
No, get out of town. That must have been such an awkward coffee room at that office.
I mean, it's a real anticlimax, isn't it? If you think, oh, I've proved you can do it in only 49. Can you believe 49? 49 palindromes, all you need. Then very shortly after that, so someone says, yeah, it's just 3.
Fantastic. So if people want to go find the original paper, they'd need to Google this, and these are the authors. I've seen you've made this program yourself, which is lovely. Is this available to people to play with at home?
Yeah, sure.
Fantastic. Link below in the description. I'll make sure you can get that. That's lovely. Looking at the things you got up on your screen here, though, Christian, about how we're counting how many different ways there are to make other numbers out of different subsets. Coming back to the prime numbers, you said that we think every number can be written as the sum of 2 primes. Goldbach conjecture. I've got 10 quid on it. But can you tell us a little bit about the weak Goldbach conjecture?
Yeah, so the weak Goldbach conjecture is a little bit weaker than the Goldbach conjecture. It's not quite as strong. It gives itself a bit more wiggle room. It says that you can write every odd integer as the sum of 3 primes.
Hey, number of the episode.
It was proved in 2013 by Harold
Hey,
Hofgott.
maths happens every day. Isn't that lovely? All right, let's move on to our next segment then before we run out of time today, and that is Gizvites sequence. So we are looking at our online encyclopedia of integer sequences, the way we finish every episode. So in Gizvite sequence, AO90822, we are starting with the number 1, as all good sequences should, and then every new term, every nth term, I should say, is going to be the largest number such that the previous word is of the form x, y to the power of k. So that is the all of the numbers before this term number should have something at the start, but then a repeated part y. So a sense of periodicity, if you like, in the sequence up to this point. Another way of describing it then is the maximum number of repeating blocks at the end of the sequence so far. And I thought we could play a quick game of Make That Sequence. So for my contestants tonight, I'm going to be asking them to play a game of what comes next in the sequence. Everyone's favorite game, you can play at home. The sequence is going to start with a 1. Christian, what is the largest number of repeating blocks so far?
1.
Very good, correct. Hope, how many repeating blocks can you see?
2.
You can see 2 of them because there's a 1 followed by a 1. Christian, your turn.
1.
Indeed. Hope.
1.
Is correct. Yeah, let's play this to sudden death, shall we? Christian, your turn.
So we're only looking for blocks on the end.
We're only looking for the blocks at the end of the sequence.
2.
There are 2. Yeah. Hope.
1.
Oh, I'm afraid it's not 1 anymore. Can you see them? We've got 1 here. We've got another one here.
Okay.
It's a 2. Ah, no. And I'm sorry we were playing sudden death for that. So we're going to have to stop that round there. And instead, look ahead at all of these numbers. Hey, look at that. What can we see? So as with most of my favorite sequences in the online encyclopedia of integer sequences, they are always just 1s and 2s, or there's 1, 1, 1, 2, and then suddenly into the billions. But this is one of our small sequences that never seems to grow. What do you notice and what do you wonder?
No 4.
No 4s. No, certainly not on those first random block of numbers that I copied and pasted in. So when do you think the first number 4 should appear? How long do you reckon you have to wait? Is it more than 20, more than
box you
30?
put in there is a big hint.
So it's a big number, that, isn't it? Hope, I'm going to press you for an answer. Your PhD is going to depend on this. When does the first 4 occur? Oh, I can hear the countdown music. Ah, it's at 220. Not actually that big. I tricked you. But 220 still seems like quite a long way into the sequence.
Mhm.
So when does the first 5 appear?
This is the one that's too big, sure.
This is going to get big. This is possibly the slowest sequence I've ever dealt with. In all of the 3 episodes that we've been running this show so far. The number 5 first appears at 10 to the 10 to the 23. That is massive, which means someone has counted them. And that's always a fun job to make a computer do. So here's a proposition for you. I'm going to say that every single positive integer will appear in the sequence somewhere. Do you think that's true or false?
I'd be surprised if it was false.
Yeah, I agree.
Yeah, it almost has to, because we are going to be able to always find another term in the sequence. So the sequence should carry on infinitely. And if I say that we are only allowed to use the numbers 1 to n, there's not an infinite number of ways that you can keep combining those 1s to n before you eventually start to double count them. Not a very rigorous proof at all, but it's intuitive to say that it will carry on forever. So maybe I could ask you if you would like to take any kind of guess at just the kind of shape of the function of when we think the number n appears in the sequence. So obviously you can't guess the number, or you won't be able to guess the formula, but what kind of shape of formula do you reckon you're expecting to see here?
Am I allowed up arrows in my formula?
Only if you can tell me what an up arrow refers to. So if
An
I
up
said
arrow sort of
n
it abstracts the idea of addition to multiplication to exponentiation. So
the one after exponentiation.
Yeah, so 1 up arrow I think is exponentiation. 2 up arrows is like 2 to the x to the x times.
Okay, so as in you're saying it might be n to the power of n,
No, it would be like n to the n, like n superscripts.
as in n lots of n to the
Yeah.
n. That's too big. That's way too big.
Okay.
It is smaller than that. And in fact, I don't know the notation for this one, but I'm going to invent a bit of notation on the fly as we go and say it should be this up arrow with a dot underneath.
Right.
Why might I be invoking this symbol?
Factorial somehow?
I'll give you a clue. I'm going to redraw it. So I'm going to draw it like this and then put the top arrow up. You said factorial, Hope. What are you thinking?
Something with an exponential and a factorial in it.
Oh, I wish you'd been more confident with your answer because you'd have been exactly right. Yeah, this is almost like the factorial equivalent of an exponentiation. This nth order string of to the powers of, which I realized a moment ago I said was definitely smaller than
No,
the up
that
arrow
is
that you
absolutely
mentioned.
what you need up arrows for.
Is it definitely smaller than just n up arrow?
I mean,
Because
yeah, you replace all
these
of your
should all
numbers
be
with
n's,
n's, then you
shouldn't
get n
they?
up arrow and up n.
Yeah. Okay. So is this a bit of notation that already exists that you're aware of?
Yeah, that's Knuth's up arrows.
Knuth up, as in this one here.
Oh, sorry, no. Well, that's just lots of exponentiations. That's
But how would you like the factorial symbol is so beautiful that it shows you the sequence up to the value n. How would you represent that with exponentiation?
I'd use an up arrow. Sorry.
Lovely. So to finish the episode off then, we're going to take a vote on what we think is the most interesting number that we've ever talked about so far. So the options are 1 or 2 or 3. In last week's episode, number 2 eclipsed number 1 as the most interesting number so far. So really, I'm asking you guys, do you think 3 is more interesting than 2 or less interesting than 2?
I think it's much more interesting than 2. Lots of stuff breaks when you go from 2 to 3.
I mean, 2, we had a big conversation about parity and odd and even being important properties. No one ever talks about
Everything,
3, the
if
number.
you're sticking with 2s, everything goes okay. It's easy street. Once you've got 3 choices for things, or once you've got 3s involved, life's hard. I mean, the number of not theorems that don't exist yet, I think, is proof of that.
Okay, so you're saying it's like the number 2, but more metal.
Yeah.
Right? What do you reckon?
I think I would go 3 over 2, certainly. There's kind of a running joke in set theory when people are sort of proving things that kind of have infinite number of cases that you prove it for 1, you prove it for 2, and then you prove it countably many times. But in the realm of the finite, I'm a big fan of 3.
All right. Okay. Well, I think the 3s have it. It's the most interesting number we've ever talked about. Please let us know in the comments what you think about the number 3 and any of the other important facts that you think that we missed talking about today. And so that brings us on to the last part of tonight, which is where we get to talk to you about our projects and what we'd like to get involved with and share with you. From me, the biggest thing that I'd like you to get involved in is this project that we're doing right now. So this chat show, Unnatural Numbers, is open to anyone and everyone to come on, have a chat with me and other guests to talk about maths. If you'd like to get involved and have a go at public speaking, let me know and I'll link you into the project. The link is in the description below. Please do get involved and do some maths out loud. I also do a maths history podcast if you're interested. Christian, have you got anything to tell us about what you're working on?
Well, the thing I pluck out of my vast backlog of projects today is a few years ago, I got fed up of just having a list in the back of my head of weird notation in maths or things that don't quite work. So I set up a website called whystartat.xyz. And what I wanted to do was like, why do we use the letter X as our first variable name? Why do we go XYZ? Why is it that sine squared of X means something different to F superscript 2 of X? That notation just doesn't make sense. So really, I wanted to write down all of those kinds of things that don't make sense or are annoying and that. So have a look at that. If you've got something that's always annoyed you about mathematical notation or mathematical language, please either add it in yourself or send me an email and I'll add it to that site. I want to have a big compendium of If anybody ever says that math notation is beautiful and it's a systematic way of looking at things, I say no, it's not.
It's just made by people, isn't it?
It's made by people. It makes even less sense than spoken language.
Fantastic. And is the up arrow factorial equivalent in your list?
It will be shortly.
Let's get that in. Lovely. Hope, what are you working on that you'd like to share with people?
So for my day job, I'm doing a PhD in set theory. So if you're someone who is interested in large cardinals or the axiom of choice, I always love chatting maths with people. But a project that I maybe point people towards that I'm currently working on and hope to have launched very soon is a science communication project that I'm doing. I kind of want to get my hands dirty with doing more science communication, and I'm exactly the kind of generation of PhD student who was raised on things like Numberphile and by heart. So I'm in the midst of starting a YouTube project where I communicate some fun maths kind of in the style of some of my maths YouTube heroes and tell the audience about what I liked about communicating in that style. So we can drop maybe my Blue Sky in the description, give me a follow, and I'll be posting some news about that shortly.
Fantastic. Yeah, so you can find Hope on Blue Sky in the description. I'm also in Blue Sky in the description. Christian is the entirety of Mastodon. He is the Mastodon overlord, and you can find that in the description as well. All right, fantastic. Well, it's bye from me.
Bye from me.
Bye from me.